back to Easy High School Physiology. This is Dave, and we're about to embark on Module 13, the ear and hearing. I just want to remind you that Module 12, we did the eye and seeing, and the module before that was the female reproductive system, so be sure to see those modules. So today, the ear and hearing, and I'd just like to remind you that the hearing is one of the senses that we're familiar with, that we see here: seeing, hearing, smelling, tasting, touching, balance, and location. Now, we've already done touching when we talked about the skin, and we did seeing when we talked about the eye. Today we talk about the ear. We're also going to talk about balance. Balance is not about hearing, of course, but the sense of balance is in the same location as hearing is. And so we're going to take a look at balance also. I'd also like to remind you that the senses that you just looked at are sort of regarded as external senses. In other words, those are the senses that send information to the brain from outside the body. We also have senses inside the body that send information to the brain. For example, about heart rate and blood pressure, breathing rate, and body temperature. And when we get to the nervous system, about the brain, which is our next module, by the way, we will be going more into internal senses and how they give information to the brain about what's happening inside the body. So, I'd like to start out going over with some vocabulary words that we're going to run into. It's only a few. Again, as I have mentioned many times before, we try to limit the technical vocabulary in this course as much as possible, because a lot of these words you can look up if you're interested in the technical term. So again, the first word we're going to be interested in is matter. And you might say, what does matter have to do with hearing? And very important. We can't hear without matter. Matter, of course, is anything made up of atoms and molecules. It can be solid, liquid, or gas. Doesn't matter. Solid is just more dense, and gases are just very thin, but it's still matter. And if you go into outer space, for example, there's no matter. There's no sound. If you ever see a movie where there's sound in outer space, they're making it up. Okay. Also, for sound to happen, matter has to be disturbed. And I'm going to start out our module today with a couple of kind of questions. I'm going to make a sound. I'd like you to try to guess what this might be from. One more time. Okay. We have another sound. Listen to this one. Guess what those might be? Well, I'm going to get back in a few minutes, and we'll see what those are. Both of those sounds were generated by disturbing matter. Vibrations. When matter is disturbed, that matter vibrates. In other words, it goes back and forth a little bit. And that back and forth movement transmits what we call sound. Frequency means how fast or how often these vibrations happen. They can be and it's usually per second, like 10 times per second, 100 times per second, 1,000 times per second. That would be the frequency of sound. That takes us to, I can't read this, it's upside down. Oh yeah, I'm sorry. Vibrations per second. This is what sound, and by the way, other things, are measured in if they produce waves. And we're going to take a look at waves in just a few minutes. Vibrations per second. We also call these hertz after a famous scientist So if we're talking about 10 vibrations per second, we'll say 10 hertz. 100 vibrations per second, 100 hertz. And capital HZ is the abbreviation for hertz. Auditory canal. This is the part outside of the ear that leads to the ear from the outside world. All right, and we'll take a look at that in a minute. And finally, eardrum. This is the thing inside near the ear that actually part of the ear that vibrates as a result of these vibrations set up by the sound. So, with all that in mind, let's take a look at our first picture. Oh, by the way, what did you think the first sound was? Here it is. It's just the top of a pot, the lid. The second vibration was this ruler, which I flipped like that, and it vibrated back and forth like that. I'll do it sideways so you can see. All right, like that. How many got that right? Raise your hand. Okay. So we're going to take a look at sound itself for a few minutes before we get to the ear. And if you look at this picture, you'll see a ruler, or maybe a piece of wood, held down by a weight on a table. And someone comes up and flips this ruler, makes it go back and forth like that, like what I just did. All right? Now, what a vibration is this. When the ruler goes from here and back to here, that's one vibration. Here, back to here, another vibration. Here, back to here, another vibration. Okay? It's got to go all the way over here and back to be a vibration. All right? Now, let's look at something interesting. Let's turn this vibrating ruler sideways, and we're going to pretend there's an ear over here. Someone is standing there here listening. These are air molecules, okay? Now remember, air is also matter, even though it's very thin. And as this ruler vibrates back and forth like this, when it vibrates this way, it pushes these air molecules together, makes them dense. And as the ruler vibrates back the other way, it pulls the air molecules apart, pushes them together, pulls them apart, pushes them together, pulls them apart. So as these air molecules go toward the ear actually hears them first pushed together and then pulled apart. Pushed together and then pulled apart. All right? Now, if we try to show that in a spring, it would kind of look like this, where this is the dense part of the spring here together is the part where the air molecules would be pushed together, and where the spring is pulled apart out here is where the air molecules would be pressed apart. Okay? Using the same idea, we have our next picture. Again, the spring, and here is where the air molecules would be pushed together. Here's where they're pulled apart. Here they're pushed together. Here they're pulled apart. Here they're pushed together, and here they're pulled apart. Now, I want to show you something very interesting. If we take a pen and actually show what this is in a wave pattern, it would look like this. In other words, the part where the air molecules are pushed together would be the high point of the wave. I got that a little bit out of whack there, but you see the idea. And then when the wave goes down like this is where the air molecules have been pulled apart. So here's the wave pattern that you could actually see in the ocean or a lake, but you see it also in air, because as air is disturbed, there are places where the molecules are pushed together, pulled apart, pushed together, pulled apart, and so on. All right, so that is what gives us our familiar wave pattern that we see here, that I tried to draw but didn't do a very good job. This person did a very good job. Here's where the air molecules are pushed together, pulled apart, pushed together, and so on. Okay. In this picture, this is the last picture we'll show about sound, and then we're going to head toward the ear. Let's see if we can squeeze this in. We see up here what's called a tuning fork right here. Tuning fork is a piece of metal that you can disturb by hitting it against something, and then it vibrates very quickly like that. And as it vibrates, it disturbs air molecules nearby, which will come over and disturb the ear. All right, so that's how sound gets from a place where it's generated to a place where it's heard. Most of you have probably been underwater, maybe in a swimming pool, so you know that liquids transmit sound, and we know that air transmits sound because that's how we usually hear, is something is disturbed, the air is disturbed, and the air molecules strike our eardrum. And that's kind of where we're headed right now. Okay. We're going to take a look at a few more vocabulary words before we take a look at the ear. And we see here, it's a funny word called ossicles. And this just means the three bones in the middle ear. We're going to take a look at those in just a minute. They have fancy names, but I'm going to avoid that right now. Ossicles equals the three bones in the middle ear. Connecting tube. There's a tube connecting the middle of the ear with the back of your throat. All right? It's called the eustachian tube, but we're going to call it the connecting tube. And it helps to equalize the air pressure that's inside the middle ear. And we'll take a closer look in a few minutes. Air pressure definitely affects the ear. If you've ever gone up in an elevator or gone up in the mountains or where the elevation changes fairly quickly, you'll notice that your ears pop. And that's because of the difference in air pressure on each side of the eardrum. And we're going to take a look at that in a few minutes. Semicircular canals. This has everything to do with balance and nothing to do with hearing. And it just happens to be in the same place. And we're going to take a look at that in a few minutes, how we sense balance. Decibels. The loudness of a sound is measured in something called decibels, and it's abbreviated small d, capital B. Vestibular sense. This is a fancy word for balance. What is your sense of balance? The vestibular sense. Okay. So, with that in mind, let's move on to our next picture. We're going to start with this one. It's fairly small, but we're going to get into a bigger one in just a minute. I'd like to show you the different parts of the ear. And here's the outer ear, of course, where the air molecules come and gather and then are focused into what's called the auditory canal right here. Okay. And here's the eardrum right here. We'll see a larger picture in a few minutes. The eardrum is what vibrates because of the vibration of the air molecules. Now, everything from the outer ear up to the eardrum is called the outer ear. Okay? Then we have, on the other side of the eardrum, this area right in here, extending down this way a little bit. This is called the middle ear right here. And then these structures over here are called the inner ear. So just like the skin had 3 layers, guess what? Hearing has 3 layers also. Again, the outer ear, the middle ear, and the inner ear. Okay? And we're going to take a closer look at that in our next picture. Yeah, this is a good one. You can see we're getting a little bit larger here in our pictures. Here's the collecting ear. It's called the pinna, but that's not important. Here we have the auditory canal. It's only about 1 inch long, about 2.5 centimeters. And then it's so hard to see right here. I should have my glasses on. Then we have, the eardrum must be right here. And the eardrum vibrates. And then we have the middle ear here and the inner ear over here. This is that connecting tube that I told you about, connecting the back of the throat, which is right here, to the middle ear, which is here. The middle ear, as we'll see in a minute, is filled with air. So the air is free to pass from the back of your mouth, back of your throat, up into the middle part of your ear. Okay. Welcome back. Okay, there's a reason that I gave the gong there, and it has to do with this picture right here. And there's an enlarged picture. This shows part of the outer ear coming. This is the auditory canal, and here's the eardrum, all right? So that's the outer ear. Here's a really nice shot of the middle ear. Like I said, it's filled with air, and it's got 3 bones. One bone is connected to the back of the eardrum here, right here. The second drum, it comes up this way. The bone. This bone is connected to the back of the eardrum, which is connected to this bone, which is finally connected to this bone here. 3 bones, 1, 2, 3. Now these bones, when the eardrum vibrates like this, they also vibrate, and they transmit that sound to the snail-looking structure that we're going to take a look at in just a minute, which has to do with hearing. These bones amplify the vibrations by about 20 times, because when this last bone pushes against this snail structure, it has to make the fluid inside move around. So you have to have quite a bit of force. And that's what these 3 bones do. They increase the force of the vibration to push against this snail-like structure called the cochlea, which we will see in just a few minutes. Okay, very good. By the way, again, this is all air in here. This is the connecting tube going down to the back of the throat, that it doesn't show it here. All of this, by the way, is bone. This is all bony material here that the ear is found in. All right. This structure right here, notice it comes out of the bony area and it connects to the back of the eardrum. This is a safety measure that Mother Nature has put in. If someone comes right up to your ear and shoots a gun, a pistol, for example, right next to your ear, this eardrum is going to vibrate like crazy. And in fact, it might even break or perforate. So if something very loud comes in like that, this muscle here pulls down on the eardrum and dampens it so that it doesn't vibrate too much. So this is a safety feature right here for any loud sounds coming into the ear. Okay, good. Now we move into the inner ear. Again, we have the outer ear here, the middle ear here we just looked at. Here's that tube going to the back of the throat, okay? By the way, let's talk about that tube to the back of the throat for a minute before we get to the middle ear. This tube is to equalize the air pressure. Again, we have air inside here, we have air over here, and it's separated by the eardrum here, the tympanum. This tube here, the eustachian tube, connects this amount of air with the air at the back of your throat. So that when you swallow or when you are not swallowing, the air is free to move back and forth and equalize the pressure in both areas. Again, when you go to higher elevations, what happens is that the pressure is less outside here because you're at a higher elevation. The eardrum has a tendency to press outwards this way, and it's only when the air pressure equalizes that the eardrum pops back in place, and you hear that as a popping going on. By the way, here's another little piece of information. In babies, it's frequent that they get ear infections. And the reason is that the germs that could be in the back of the baby's throat have a short distance to go up this connecting tube to the middle ear and produce an infection. As we grow older, this tube becomes longer, and it's harder for the germs to come from the back of the throat up into the ear area and cause an infection. So that's just kind of an interesting sideline there. Now we're going to put our attention to the inner ear, which is this part right here. The inner ear is made of this snail device here called the cochlea, which has to do with hearing, and this device up here, which has to do with balance, okay? When these three bones vibrate, they're pressing against this snail structure here, and inside, as we will see, is a liquid. It's thicker than water, and it's free to kind of slosh around, this liquid is. And when these vibrations push against the liquid vibrates around just like water in your bathtub might kind of move around. And as that happens, little hair cells at different points in the snail hair vibrate or are made to move back and forth. And when those hair cells move back and forth, they're connected to nerves which generate electricity, which send a message along the auditory nerve, which is here, to the brain. It is the brain which interprets what we hear, all right? And the physical action of hearing, of sound, has to be translated into electricity before the brain can understand it. Okay. Now, let's take a look. If we took that snail-like structure called the cochlea and we expanded it out straight so it's not a snail anymore, this is kind of what it will look at like. Here's the outer ear again, here's the middle ear, and here's the cochlea, but we've stretched it out straight, okay? And notice little hair cells along the way here at different points in the cochlea, all right? And there's a fluid in here that's thicker than water, and the fluid can move around depending on these bones pushing in on the cochlea here and making that fluid move around. As the fluid moves around, it stimulates these little nerve cells, little hair cells, which kind of move back and forth. That stimulates nerves, which send a message to the brain through what's called the auditory nerve. And then the brain interprets what you are listening. The high-frequency sounds, high-pitched sounds, are detected down at this part of the cochlea, and the low-pitched sounds are connected further on down the cochlea here, all right? People can hear a frequency or vibration of about 20 times per second way down here. That would be like, oh, very high frequencies, about 20,000 times per second up here. Ah, like that. And remember, animals like dogs can hear well above 20,000 hertz or 20,000 vibrations per second. So anyway, this is what the cochlea is when it's spread out, and we can see what it does. Otherwise, it looks like a snail. Okay? All right. We're going to change our attention to balance now. And as we see in this picture, we already looked at the snail. We spread it out straight. Now we're going to look at this part right here. These are the semicircular canals, and they have to do with balance. Notice they're close to the hearing, but they have nothing to do with hearing. Okay? And we're going to take a close look right here. Here's the cochlea, that snail device we just looked at that does have to do with hearing. And these are the semicircular canals. There's 3 of them. And these canals are filled with a fluid similar to what we found in the cochlea. The fluid is free to move around inside these canals. And the canals also have little hair cells that detect the movement of the fluid and send that message to the brain. Now, here's what's interesting. Each of these canals is at a 90-degree or a right angle with the other one. So this is in one plane, this is in another plane, and the third one is in the third plane. So no matter how your body is moving, whether forward, to the side, or up and down, one of these canals will detect that movement, and the fluid inside will move around accordingly and stimulate those little hair cells, and a message will go to your brain telling the brain about your balance, where your head and your body is in relation to the outer space. Okay? This is called the vestibular sense, and actually this information goes to a different part of the brain than the hearing information. Okay. Let's see, here's another nice picture of the semicircular canals. Again, here's the cochlea for hearing. Here's the auditory nerve, which also carries the vestibular information. Here's the semicircular canals. One canal here, one canal here, and then another canal coming up here like that, at 90 degrees to each other. Okay? And this detects your sense of balance. The last thing we're going to look at today, one of the words we looked at in our vocabulary was decibels. Sorry, this picture is so small. It's the only one I could find. Decibel is a measure of loudness. Now, here's some examples of different kinds of sound and the decibel levels. Usually, if you're just talking with somebody in a room at a regular voice, you're at probably about 25 to 30 decibels. If you're outside doing yard work, maybe with a lawnmower, that might be 80 or 90 decibels. And if you're standing behind a jet airliner at the airport, that could be like 140, 150 decibels. So, again, this is the loudness of sound. It can be measured with scientific instruments, and it's called decibels. Okay? So, with that, I think we're going to wrap up hearing and balance. I hope you've enjoyed learning about it. Our next module, we're going to delve into the nervous system, the brain and the spinal cord, and all of the things that regulate the activities of your body. And I hope you will come and join us then. Until then, here's Dave saying goodbye.